While we're at it, let's take a quick look at the calendar. What's that? Yeah, where have you been? This big stack with all that line of people that were coming up here. Okay. 6-1 is not that hard, but we're gonna kind of investigate that today. Here's what I hope. We are going to cover some difficult things in Chapter 6. You'll notice that the next test isn't until about 2 weeks after we come back from spring break. So we've got about a month to cover this. That's kind of stretching it out a little bit. This is a very important chapter and very important topics that we'll cover that'll relate to stuff that you do in 1050. Here's what I'd really like to do. I'd like to have 6-3 finished up the day before here, so that if you've got homework in other classes, maybe we'll make this Friday just a work day or something like that. And so you can get stuff done, walk out of here, be in good shape. I'd really like to be done with this, have it graded and everything before you leave. So when you leave, you can just enjoy the spring break, have no math to worry about or anything like that. If you've got college classes, they go till all the way to that first week in May. Worry about those rather than a high school class like this. Okay, so let's try and push this a little bit, get everything finished up so you can have a nice spring break and then focus on things that are a little more important. Okay, sound good? Because you're all going to be taking either 1010 again or you're going to take 1050 or something like that. So there's plenty of time to improve there. So you guys do enough school to make sure you have a good spring break. So let's push through this stuff in Chapter 6 and go from there. All right. So Chapter 6 is on a bunch of functions, inverse functions, exponential functions, logarithmic functions, different things like that. Some really cool properties with these. Also, they're really heavily used. If any of you are interested in going on in math and becoming an engineer or anything like that, you've got to take a lot of math, and these are really, really important functions. Okay? So in Chapter 3, we talked about the fact that a function is a set of ordered pairs where each x corresponds to only one y. So let's remind ourselves of why dealing with a function was important. We liked things that were functions. So the first example that we're going to use is we're going to relate the number of hours you work with how much you get paid. So let's say, for instance, you get paid $10 an hour. So the domain are the things that you plug into a function, and the range are the things that you get out. Well, if we're talking about how much you get paid, you first have to work a certain number of hours, and then you're going to get paid. So let's say we work an hour, we get $10. So these two correspond to each other. Let's say we work 2 hours. We get $10 an hour, so that's going to be $20. Say we work 3, that's going to be 30. Let's say we work 4, and that's going to be $40, right? So we kind of think of a function like a machine. You plug something in, and it does something to it, and it spits it out. So you plug in hours that you work, and what comes out is your pay, the dollars that you get paid. All right. It's just Mr. Jolly. Okay.
Yeah, I've been locked out. Are you sick too, Mr. Jolly? Pardon me? Are you sick too? No. I'm just in here because...
I'm not sick either if you're worried about me, but apparently you're not. Okay? Okay, so the reason we're interested in a function is if this were you, you'd want to know that when you work an hour, you get paid $10. When you work 4 hours, you get paid $40. Okay? Functions are very, very consistent mathematical machines, very consistent mathematical rules. If you dump in the same number of hours this week as you did last week, you're hoping you get paid the exact same amount. Okay? What would not be good is something like this. So let's mess this up just a little bit. Let's say next week you work 4 hours and in your paycheck you get paid $10. Do you like that? Not at all. Okay? Now, you wouldn't argue if this happened, would you? 1 week you work an hour, you get paid $10. The next week you work an hour, you get paid $40. That wouldn't be too bad. But in either one of those cases, somebody's going to be upset. Either you're going to be upset that you didn't get paid enough, or your boss is going to be upset that he paid you too much. Okay? Now, let's take a look at the graph of these points right here. So again, we've got this set of ordered pairs, and let's take a look at where there's an issue, and let's take a look at that inconsistency. So if I work 1 hour, let's scale this as 1, 2, 3, 4, 5, and let's scale this in 10. So this would be 10, 20, 30, 40, and so forth. Wow, that's the most blushes I've ever gotten at one time. I'm still not getting sick though. Okay? All right. So if we graph 110, that would be right here. If we graph 220, that would be right here. If we graph 330, so this should look kind of familiar. This is a nice linear pattern. Okay, those are the 4 points that we wrote down originally. Okay, now let's write down the ones that really messed this up. So I'm going to put this one in red. Let's work 4 hours, but only get paid $10. Where does that go on the graph? 4 and 10, right there. Okay? And let's graph this other one. You work 4 hours and you work 1 hour and you get paid $40. So that would be right here. Okay? Do you remember this from Math 1010 and from Chapter 3 in this class? Okay, what's wrong with this? It doesn't pass the vertical line test. Okay, these 2 points are messing things up. Okay, they don't allow this to pass the vertical line test. So whenever we have a function, it has to pass the vertical line test. Okay, so those 2 mess it up. That's why we don't like those. We wouldn't want to include those. This is just fine with us. Again, it's that nice, consistent mathematical rule. Okay? All right. Now, let's talk about a one-to-one function. Okay, a one-to-one function is a little bit more special than a regular old function. Okay, a one-to-one function, each x has to correspond to only one y. Okay, that means it passes the vertical line test. But we're going to add one more condition here. Okay, that part makes sure that it's a function. Now we're going to make sure that it's a one-to-one function. Okay, and that part is each y can correspond with only one x. Each y can correspond with only one x. What that means is it has to pass the horizontal line test. So we're going to take a look at 2 fairly familiar functions, ones that are easy to graph, and we're going to figure out which one's one-to-one and which one's not. So let's graph a parabola, just that standard old shape, squaring function. So we get this graph right here. And we could label those points if we wanted to. Okay, there's the graph. And then let's graph 4x plus 1. So the plus 1 moves the graph up. The 4 makes the graph steeper. It makes the points 4 times as tall as they used to be. So we're going to go like this. And then the slope would have us looking like that. There we go. Okay? All right. Any questions? Everybody got the graphs okay? Let's see if I can make it that big. Okay. Are they both functions?
Yes.
How can you tell? They pass the vertical line test. So if I take any vertical line and draw it, it only intersects each one of those graphs in one place. Okay, so each one of these is a function. Okay, are they a one-to-one function? Are both of them one-to-one functions? Nope. Which one's not? Okay, the x squared is not. Okay, and let's look at 2 specific points right here. Okay, this point is 2 comma 4, and this point is negative 2 comma 4. They are on the same horizontal line. So if I take horizontal lines, no matter what horizontal line I do here, it only intersects it in one place. So this one is 1 to 1. This one is not 1 to 1. Not 1 to 1. Okay? So you can tell really easily just by looking at a graph whether or not the function is 1 to 1. If it's a function, it passes the vertical line test. If it's a 1 to 1 function, it passes the vertical line test and the horizontal line test. Everybody okay with that? Okay. Can somebody tell me what the word inverse means? Shane. Okay. Means opposite. Can somebody come up with another word? Okay, reciprocal, depending on what the function is, that could be an inverse. Okay, this is the way I'd like you to think of an inverse. An inverse undoes. Okay, so the word inverse means it undoes it. So what would you say the inverse of multiplying by 2 is? Dividing by 2. It will undo multiplying by 2. What's the inverse of subtracting 7? Adding 7. Okay? They're kind of opposites, but sometimes in math we get confused with opposite. Like what's the opposite of 9? Negative 9. Okay? So you'd want to be careful with that. They are related. A better way to think about inverses is they undo each other. Yeah.
So it's like the verb versus a noun.
Yeah, I suppose you could kind of think of that. Yep. Instead of the opposite, it undoes. It's active. Okay, I like that. Very good. Think of it as a verb. That would be fine for you English people out there. Okay, now this is a process that you may have seen before. We can actually find the inverse of a function, and here's how we do it. Since we're interested in undoing something, we normally plug in x's and get out y's. We're interested in kind of doing that in reverse. So we kind of reverse that process, and the way we do this is we switch the x and the y, and then we solve for y. So we're going to take a very easy function right here, one that we already graphed up above, and we're going to find the inverse of that function. You'll notice that this function right here, we multiply by 4, and then we add 1. So somewhere we're going to have to undo multiplying by 4, and we're going to have to undo adding 1. Okay, that on a simple function like this, you could probably think your way to what the answer is. So the first thing we want to notice is this is written in function notation. So I'm going to write it as y equals 4x plus 1. So that's the original function. Then I'm going to change colors here, and we're going to find the inverse. So the first step to finding the inverse is switch the x and y. So wherever there's an x, we're going to write a y. Wherever there's a y, we're going to write an x. So I'm going to write x equals 4y plus 1. What's that?
Is that it?
Almost. That's step 1. Now we just need to do step 2. Step 2 is solve for the y. In other words, get the y all by itself. So the first thing I'd want to do if I were getting y by itself is I'd get rid of the 1 by subtracting 1. These are not like terms, so I need to write x minus 1 equals 4y. And then how do I get rid of the 4 in front of the y? Divide by 4, because it's timesing by 4, right? So I'm going to divide this side by 4 and divide that side by 4. Now, what I get is I get y equals x minus 1 all over 4. Now, that big long fraction bar is important because we're doing the x, subtracting 1 from it, then we're going to divide by 4. Okay? So, if this is the original function, now again, this was written in function notation. If that's the original function, we found the inverse. The way we'd write the inverse in function notation, it would look like this. We'd write g with a negative 1 that looks like an exponent, but it's not. I'll explain more about that in just a second. So this would be x minus 1 over 4. Okay? That is the inverse. And the way we say this is we say g inverse. So whenever you see what looks like an exponent of negative 1 over a function, it does not mean that it's a negative exponent. It doesn't mean do this. Everybody watching? This does not mean that. It doesn't mean reciprocal like a normal negative exponent does. Okay? That's the only exponent that's weird like that. This is just notation. It is not an exponent. Okay? So please don't confuse that. Whenever you see this, you literally read it G inverse. Okay? So if I see this, what do we say there? F inverse. Okay? You don't say F to the negative 1. Okay? F to the power of negative 1. You don't say that. It's just F inverse or G inverse. Everybody okay there? It's just mathematical notation. Okay, now we're going to take a look at this. I'm going to graph the original one in red. We already did this a second ago. So this one crosses at 1 and the slope is 4. So that graph looks like this. Okay, and I'm going to label that. That is the function g of x. Or sometimes I'll just write that's the function g. Okay, that's the name we gave that. Any questions there? Okay, let's graph G inverse. Now G inverse is a little bit weird because it's got this fraction here. We could rewrite that if we want. Again, using the properties of fractions, we could write this as, everybody watch, x over 4 minus 1/4. And it might be even easier if we wrote this. Whoops. 1/4 x minus 1/4. Is that okay? Because all I did is break it into two pieces, and then what I did is I pulled the numbers out in front. There's a 1 on the top and a 4 on the bottom, so I write that as 1/4 minus 1/4 x minus 1/4. Now, why is this helpful right here? It's easier to graph it. It's in slope-intercept form. So where does this one cross the y-axis? Negative 1/4. So I'm going to blow this up just a little bit more. It's going to cross at negative 1/4, so about right there. Fractions are pretty tough to graph, so we'll just kind of eyeball it. And then what is the slope? 1/4, rise over run. So we rise 1 and we run 4. So we're going to rise 1, go to about right there, and then run 1, 2, 3, 4. So about there. Down 1, and then back 1, 2, 3, 4. So about right there. So if this one is a graph of G, how would we label this one? G inverse. Okay? Any questions there? Okay. Please watch. This is going to come up numerous times. You can look at some graphs and you can tell whether or not they're inverses by seeing whether or not they're reflections across the line y equals x. So if I draw this line right here, y equals x, and I tilt my head just a little bit to the right, do they look like they're reflections of each other? They do. Okay? They look like they're reflections. And we're going to see some other graphs that it'll be a little easier to see. Okay? So these two are inverses of each other. And we can tell because they're reflections across the line y equals x. And, my gosh, we did all the algebraic work to actually find that. Okay? All right. Any questions there? Okay. Let's take a look at this one right here, because this is the big idea. This is conceptually what's going on, and if you understand this, then you're going to be in good shape in the long run. Here is what inverse functions do, and this is why we describe them as they undo each other. So here's what happens. I'm going to take a number, we'll call it x, and I'm going to plug it into the function f. It's going to do something. And what's going to come out is f of x. So our rule is f. We plug an x in, we get out f of x. It's like plugging in an x and getting out a y. Remember, y is the same as f of x? But then we're going to plug that into its inverse. So this one does something. What does this one do? It undoes. So if we plug in an x, we get out an f of x, and then we plug it into something and it undoes that, we should get right back to where we started with. We should get right back to x. So I've got some pretty simple examples here, and we'll do these numerically so we can see what goes on with these. Okay, so here's the function. What undoes multiplying by 2? Dividing by 2. So its inverse would be x over 2. What undoes dividing by 3? I just gave away the answer. What undoes dividing by 3? Timesing by 3. So its inverse would be 3 times x, or 3x. Okay? What is the inverse of multiplying by 4 and then adding 1? X minus 1 over 4. Okay, now, we found this function just a second ago, right? Or this inverse function. Is everybody with me? Okay, I want you to think about this for just a second. You can't do this on everything, but think about what happened here. The first thing that happened when we plugged in a number is we times by, I'll use this symbol, times by 4. And then what's the second thing we do? Add 1. Well, if you're going to undo that, doesn't it make sense that you'd undo it in the opposite order? So the very first thing you'd do is what's the opposite of adding 1? Subtracting 1. And what's the opposite of timesing by 4? Dividing by 4. Look what happens here. Plug in a number. What's the first thing that happens to it? Subtract 1 and then divide by 4. Okay? So on very simple functions, you can actually think your way to what the inverse would have to be. So let's look at some numbers. Okay, let's say we plug in a 3. Plug it into 2x. What comes out? A 6. Let's plug that in here. What's 6 over 2? 3. Start with 3, end up with 3. If they truly undo each other, whatever this one does, this one undoes. So if we plug in, let's pick a number that's divisible by 3. Let's say 21. If we plug that into this function, what comes out? 7. If we plug that in here, what comes out then? 21. So we started with a 21 and came out with a 21. They truly are inverses. Now, we looked at a graph up here of these functions, and we said they were inverse, and I said how you could tell by looking at the graph whether or not they were inverses. Okay, pick any number you want. Go ahead and pick it. Put that number right here and plug it into this one. Get the number out. Put it right here, and then plug it into this one. And if you do your math right, the number at the beginning should be exactly the same as the number at the end, right? Probably 2/3 of you pick a number that you have to work with fractions, and 1/3 of you pick a number that, well, unless you're really smart, which all of you are, so maybe all of you got this. Okay? I heard somebody say the number 1, right? Okay. Let's do the number 1. If you plug in the number 1, what do you get out? You get out a 5. If you plug a 5 in here, you get 5 minus 1. 5 minus 1 is 4. 4 over 4 is 1. There we go. Did anybody have that not work out? They got a different number out than they plugged in? No? Okay, it'll work every single time. That's what inverses do. Okay? All right, any questions? Okay? Sure? Okay, let's look at a more interesting function then. This is one that you've graphed before. In fact, we graphed this yesterday on that worksheet. So this is the cubing function. So the first thing we want to do is we want to graph this. And we want to see whether or not it's a one-to-one function. So that goes through 0, 1, 1, 1, and 2, 8. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. Good. Plenty of room here. Negative 1, 1, and then negative 2, negative 8. So I'm going to label this point right here as 2, 8. I'm going to label this point right here as negative 2, negative 8. And we'll just trust that we've done a good enough job on the rest of it. Those are the only ones I'm going to label. So nice, neat graph. Okay. Is it a one-to-one function?
Yes.
Yes, it is. How come? Passes the horizontal line test. It's a function because it passes the vertical line test, but it's a one-to-one function because it passes the horizontal line test. Okay? Then it says find F inverse. So that's how we'd read this again. That's F inverse. So we come back up here and we say, all right, this is y equals x cubed. Okay, there's that two-step process for finding the inverses. What's the first of those two steps? Switch the x and y. So again, I'm going to change colors for the work on the inverse, and I'm going to write x equals y cubed. Well, this is pretty easy. All we need to do is get y by itself. So we need to get rid of the cubing. How do we do that? Cube root. So I'm going to take the cube root of this side and the cube root of this side. So I have y equals the cube root of x. Or the way we'd normally write that, since those are inverses, are this. I'd write f inverse of x is the cube root of x. So over here, and I'm going to do this work in blue, we're going to graph the cube root function. Now, isn't that one of the parent functions that you graphed yesterday? Okay, so let's go ahead and do that. So that goes through 0, 0. Then the cube root of 1 is 1. What's the next nice number to graph on the cube root function? 9 doesn't have a nice cube root, but 8 does. 8 has a nice cube root. The cube root of 8 is 2. So we go over here, 1, 2, 3, 4, 5, 6, 7. Slide over just a little bit. 8 and 2. So this is 8, 2. And it goes through negative 1, and the next nice point to graph is negative 8, negative 2. So the graph looks like this. Okay, now how did I say just a few minutes ago you could tell whether or not graphs are inverses of each other just by looking at them? They are reflections across the line y equals x. Yeah.
So all odd degree functions.
All odd degree parent functions, yes. They're 1 to 1. Yep, the even ones would not. You are correct. Right. Good there? Okay. So, take a look at this blue graph. Okay, they are reflections across the line y equals x. Is the blue graph, is it a function also? Does it pass the vertical line test? Yeah, okay. Everybody watch, please. Okay, this is why 1 to 1 is a big deal. Okay, if I took this line, say that's the line y equals 8. It only crosses this graph in one place. Okay, that's what makes it a 1 to 1 function. It passes the horizontal line test. If I take, and I'm switching the x's and y's, if I switch this for an x equal 8, okay, so that would be this one right here, that would be a vertical line at x equals 8. So if this one passes the horizontal line test, its inverse will pass the vertical line test. And that's why 1 to 1 is a big deal. Because if you've got a 1 to 1 function, its inverse will also be a function. Okay? Its inverse will also be a 1 to 1 function, or a function. So why is 1 to 1 such a big deal? Because its inverse will also be a function. Because if the original one passes the horizontal line test, its inverse will pass the vertical line test. And that's what we want. We want functions. Okay? Again, and we talked about this. What happens to a vertical line when we switch the x and y's? It becomes a horizontal line and vice versa. Okay? The domain for the original function would get switched for the range for the inverse function. Okay? All right, any questions on that example? Okay. All right. So let's take a look at these problems right here. I think you've got a few on your assignment that are this simple. It says, which of these functions have inverses that are also functions? So remember what goes on here. We switch all the x stuff for y stuff when we're finding inverses. So we switch y equals a horizontal line for x equals a vertical line. So in order for its inverse to also be a function, it's got to pass the horizontal line test. It's got to be 1 to 1. Is that a 1 to 1 function? Yep, so its inverse would also be a function. Is that a 1 to 1 function? Yep, so this inverse would also be a function. How about this? No. So this is a yes, this is a yes, this is a no. Okay, now here's why. Okay, this is just a regular old parabola. Watch what happens if I take this horizontal line. Now remember, I'm just going to reflect this across the line y equals x. Its inverse would have to look something like this. So this horizontal line would become a vertical line right there. And we talked about the fact that we can't have these 2 points stacked on top of each other. We don't like that confusion. If we go over here to 4, we don't want to wonder whether we go up here to 2 or down here to negative 2. Okay, or in other words, if we work 4 hours, we want to know we get paid $40, not $10. Got that? Okay, take a good look at this one. Is that a one-to-one function? If we had an asymptote here and an asymptote here? Yeah, if you draw a horizontal line, it's only going to cross this in one place, and it's only going to cross that branch in one place. So that one would be. Okay, so that one's a yes. Okay, how about this one right here? This is, I'm going to enlarge this just a little bit. Okay, a lot. This is half of a parabola. Is that a one-to-one function? Let's check. Just draw a bunch of horizontal lines. How many places does it cross that graph? Only one. So it is a one-to-one function. So I could also look at this if I wanted to graph its inverse. Remember, I can draw the line y equals x. And its inverse would have to be a reflection. So this piece would come over here. This piece would come here. That point would stay right there. Why does that point not move? It's on the line y equals x. So if y is the same as x, when you switch those, does it make any difference? Nope, not at all. Okay, this point would come up here, and it would be a graph that looks like this. Is that okay? Okay, if this is like x squared, what does that graph look like? Doesn't it kind of look like the square root of x? Yeah, it kind of does. Okay, so this one would be a yes because it's a one-to-one. Okay, any questions? Okay, let's take a look at the last couple examples here. It says, are these two functions, f of x equals 3x plus 4 and g of x equals 1/3 x minus 4, inverses? Do they undo each other? Okay, well, how could we check? Okay, we could actually try and find the inverse and see if it works out to be this. We could do something like this. Let's take the number 7 and let's plug it into f. What comes out? Let's see, 7 times 3, that's going to be 21, plus 4, that's going to be 25. Let's take that and let's plug it into g. Let's see, we're going to plug in a 25. 25 minus 4 is 21. 1/3 of 21 is 7. Okay. Well, that's pretty good evidence. We started with 7 and we ended up with 7, but that's just one number. Maybe it doesn't work that way if we plug in a 2 or a -10 or something like that. So that's pretty good evidence, but it's not perfect. What would be really good is if we plugged in an x and got out an x. So let's do that. If you plug an x in here, what do you get out? What do you get out? 3x plus 4. Okay? Plug it into f, you get out 3x plus 4. What are we going to do with that? We're going to plug it into g. Okay, now watch. Here's what g is. G is 1/3 times something, subtract 4. What is that something we're going to plug in? 3x plus 4. So if I take 3x plus 4 and subtract 4, what happens to the positive 4 and the negative 4? They cancel each other out. So then I've got 1/3 times 3x, and what is 1/3 times 3x? That's just x. So I started with an x, and I got out an x. Is that really convincing? I hope so, because we could choose any number we want, and it should work that way. Okay, are there any questions there? Okay, so the function should, the word is, they should undo each other. That's the way I want you to think of inverses. Don't think opposite. Okay, just think they undo each other. Okay. To check this, we can plug one function into the other and then simplify. If they really undo each other, the answer should be x, and that's what we did here. We plugged in an x, f did something to that, it multiplied it by 3 and added 4, and then we plugged that answer into g and it undid whatever that one did. Notice what it does, it subtracts 4 and divides by 3. Aren't those the opposite of timesing by 3 and adding 4? Okay. Any questions there? Okay, let's take a look at the next example. It says, given the graph is a one-to-one function, draw its inverse. You've got a couple problems like this, so all we need to do is draw the inverse. Okay, now, there's that two-step process for finding inverses. What is that first step again? Switch the x and y. So this right now is an xy pair. If we switch it, instead of being 1, 2, what would it be? 2, 1. So let's go over 2 and up 1. So that's the point 2, 1. We switched it, we reflected it across the line y equals x. If the x is 0 here and the y is 1, if we switch those, what point do we have? 1, 0. If we switch these, 0, negative 1. And if we switch this, negative 2 stays where it is because it's on the line y equals x. If those two are the same, switching them has no effect. It's still the point negative 2. So, if that was the function, this would be the inverse of the function. And do they look like they're reflections across the line y equals x? They do. Okay. Any questions? Sure? Okay, you've got a couple problems that are literally that easy. You're just looking at a graph and drawing a couple of points. Okay? All right, so let's finish this up. It says each function below is one-to-one, so I'm telling you it's a one-to-one function. Find the inverse of each function and state the domain and range of f and f inverse. Okay, so let's take a look at this guy right here. Could you graph that? Hopefully pretty easily. Let's go ahead and graph this one. I'm going to do this one in black. So this is the cubing function, and all that happened to it is we moved it down 1. So it would look something like this. And I'm going to label this point right here. This point is 2, comma. What happens when you plug in a 2? What do you get out? Normally you get out an 8, but then you subtract 1, so it's going to be 2, 7. Okay? So familiar function, pretty easy graph. I'm going to label 1 point on it. We're going to use that in just a minute, aren't we, Shane? Absolutely. Okay. So if the original one is y equals x cubed minus 1, we're now going to find the inverse. So we're going to switch the x and y. So I'm going to write x equals y cubed minus 1. So how do I find the inverse? Okay, step 1's taken care of. We switch the x and y. Now we just, second step, solve for y. So I'm going to add 1 to both sides. So this is going to be x plus 1 equals y cubed. And how do we undo cubing? Cube root. So this is going to be y equals, this would be the cube root of x plus 1. Okay, now I'm going to write it this way. If this is f, this is going to be f inverse of x is the cube root of x plus 1. Okay, now, do you know what the cube root function looks like? Shane, do you know what the cube root function looks like?
Oh, yes, definitely.
You do, okay? Looks like that, right? Okay, can somebody tell me what the plus 1 does to this graph? Charles, very good. It moves it to the left. So we're going to take this shape that normally goes through the origin and we're going to move it over 1 unit to the left. So we're going to have it go through right here. And it's going to look like this. So if this is f, this is f inverse. Now, if we truly did this correctly, if this really is the inverse, there should be a point on the graph that corresponds to this one here. What point should it be? It better be 7 comma 2. It better be 7 comma 2. Now, let's double check. If you plug in a 7, you put a 7 right here and a 7 right here. So F inverse of 7 would be the cube root of 7 plus 1. Well, the first thing you do is you take 7 and you add 1. What do you get? 8. Cube root of 8 is 2. Did we do it right? Yes, we did. Not only that, I want to call your attention to one other thing. I'm going to label this point right here. It normally was at the origin. It's now at 0, negative 1. What is this point right here on the inverse? Negative 1 comma 0. Look how the x's and y's got switched. Okay? All right. Any questions? Okay. This one isn't terribly interesting to write down. The domain for the original one, you can plug in anything you want and get out anything you want. It's from negative infinity to infinity. That's something that you wrote down the other day. Okay? Or yesterday when you did these. That means the domain for the inverse should also be negative infinity to infinity. Same with the range, negative infinity to infinity. Okay? Any questions there? Sure? Okay. All right. Let's take a look at this one right here. So here is F. Let's graph that. Notice that it's a restricted domain, we call this. We're not plugging in anything we want. We're only plugging in x's that are greater than or equal to 0. That's a fancy way of saying what? It's half of the parabola. Which side, the left or the right? The right side, the positive side. X's that are greater than 0 are positive. Okay? So it's going to be this graph right here. Except for it would be moved up 1, right? So we take that shape and we move it up 1. So we're going to go through 0, 1, and it's going to look like that. Now I'm going to label this point right here 0, 1, and I'm going to label one more. I'm going to label 2 comma. What do you get when you plug in a 2? 5. 5. Square 2, you get 4. Add one more, you get 5. Okay, I'm going to change colors. And let's find the inverse. So this would be x equals y squared plus 1. Same steps. We're going to solve for y. We've switched the x and y. Now we solve for y. It's just that simple two-step process. So this is going to be x minus 1 equals what? Whoops, y squared, not y cubed. Take the square root, and I get y equals square root of x minus 1. Now, can somebody tell me why I don't have to worry about the plus or minus here? Because these were all positive. That's why. So if you take the square root of a positive, you're going to get a positive. Okay? Let's take a look at this. Do you know what shape this is? Square root graph. What does the minus 1 do to that graph? Moves it to the right. Remember? It does the opposite of what you'd think. Whenever you change the x, it does the opposite. So this is going to be the square root graph, but it's going to be moved over to the right 1 unit. So it's going to look something like this. So this point right here would be 1, 0. And then if we did this correctly, if these truly are inverses, there should be a point of 5, 2. Let's double check. Does 5 work here? Does it produce a 2? If you plug in a 5, subtract 1, you get 4. What's the square root of 4? 2. So does it work? Absolutely. Okay, now we want to look at this, and this one's a little more interesting. Let's write down the domain and the range for the original one. The domain was only positive numbers, including 0. So that was 0 to infinity. The range was, where did we start getting answers? At 1. So that's going to be from 1 to infinity. Okay, now take a good look at this red graph. What's the domain? What are the numbers you can plug in? What are the x's you get out? Or sorry, the x's that you can plug in? They start at 1 and they go to, whoops, infinity. And what about the range? What type of y's? If we squish the red graph onto the y-axis, we get 0 to infinity. Oops, this should be square. Okay, and what I want you to notice is this. The domain on the original function is the range on its inverse. And the range on the original function is the domain on its inverse. See how these got switched? These are normally x's, they got switched for y's. These are normally y's, they got switched for x's. Does that make sense? Okay, real quick look at the last one. Let's see, we're out of time. Try and do that one on your own. We'll start with that one tomorrow. You should be able to get started on the assignment. Please make sure you bring your book tomorrow because you are going to have time to work in class. Remember, our goal is to get all this stuff done through 6-3, be all finished before you've got spring break, okay? So bring your book tomorrow.